Hello everyone. So today I'm back with another video on thermodynamics series. If you have not watched my previous videos on thermodynamics, please go to my playlist thermodynamics and do watch my previous videos. So today I will discuss about uh, constant heat capacity at constant pressure Cp, molar heat capacity at constant volume Cv, the expression of Cp minus Cv for different type of gases, ideal gases, real gases, for water, etc. And I will introduce the concept of enthalpy, and I will discuss the difference between enthalpy and internal energy. Before I do anything, I will prove a small postulate that work and heat, they are not perfectly differential quantity. Okay, so let's get started. Let me share the screen. So as I said, I'll briefly uh, describe about uh, heat and work. I have already discussed about heat and work in my first, second, third lecture of thermodynamics. Please do watch that. If you do not know what is heat and what is work and what is the first law, etc. And I have also discussed in details what is perfectly differential quantity. It has to satisfy certain conditions in order to be a quantity to be a perfectly differential quantity. So I have discussed in details in my previous videos. So please do watch that if you do not know what is a perfectly differential quantity. So today I'll try to prove the postulate. Heat and work done, they are not perfectly differential quantities. So let me write this. Heat, this is Q. You must have known if you have watched my previous videos that we describe heat as Q and work done W. They are not perfectly differential quantities. Okay? So I'll prove this mathematically. Please do watch what is a perfectly differential quantity in my previous lectures. So uh, Q and W of a system between a initial state and a final state, it depends on the nature of the process. Okay, I have also discussed about what is the expression of Q and W for different type of process. Okay, so in order to prove this, let's first suppose Q is the change in Q. The change in Q is denoted as dq. Okay. So first we'll try to prove whether dq is a perfectly differential quantity or not. So what was the first law? If you do not know, please do watch my previous videos. I will directly write the first law of thermodynamics. What was that first law? The expression, mathematical expression. So it was, so I will write dq instead of q because I am taking that changes in q is denoted as dq. So we'll write it as dq instead of q. So what was the first law? dq is equals to del u del t V dt plus T plus del U del V T dV. Okay, so now what I'll do, I'll differentiate del Q del T V. Okay, so I'm differentiating with respect to T, keeping volume constant. So what will be that? So I'm differentiating with respect to T, so dt will be 1, so that will be del U del T V. And this part will be 0 because I'm taking volume constant, so dV will be 0. The differentiation will be 0, so I can write this. So similarly, I can do the another differentiation. Del Q del V T. That is, I am differentiating with respect to the volume, keeping temperature constant. What will be that? That will be, this term will be 0 because temperature is constant, dT is 0. So it will be this one. So P plus del U del V T. Okay. So now I will do the second derivative. So differentiating with respect to volume at constant T. So what will be that? Second order derivative, del square Q del V del T. So this will be del square U del V del T. Okay, and what will be this? If I do a second order derivative with respect to T, del square Q by del T del V, this will be del P del T V constant volume plus del square U del T del V. Okay, I hope you understand these basic derivatives. These are very simple mathematics what I'm doing. If you are reading physical chemistry, you should know this. Okay, so what was my perfectly differential quantity criterion? The last criterion was it must obey the Euler's theorem. So if Q is a perfectly differential quantity, Q is a function of T and V. So in order to be Q to be a perfectly differential quantity, it must satisfy Euler's theorem. That is, del square Q del V del T equals to del square Q del T del V. This term, if these two terms are equal, we can call the Q a perfectly differential quantity. But you can see from this, we are taking the first law and we are deriving these two. These two terms, they are not equal. They are not equal. So we can say dq is not perfectly differential quantity. So q is also not this perfectly differential quantity. Okay, so we have proved this. Next, we'll prove the W. The work done is not perfectly differential quantity. So similarly, we will denote change in W as dW. So we will restrict the work to be mechanical work only. Work is mechanical work. So dW will be P dV. Okay, change in work. So we know volume is a function of temperature and pressure. Okay, so what will be dV? dV is equals to del V del T P dP. I'm sorry, dt plus del V del T T dP. Okay, so we'll just put this over here. So dW is equals to P del V del T P dt plus P del V del E T dP. So we'll now do the same thing. We'll differentiate it. So we'll differentiating this del W with respect to temperature at constant pressure. So this will be P del V del T P. And this term will be 0 because pressure is constant, so dP will be 0. Similarly, we will differentiate it with respect to pressure. So del W del P T is equals to P del V del P T. And this term will be 0 because temperature is constant, so dt is 0. So we have differentiated first with respect to temperature, keeping pressure constant, and then we have differentiated with respect to pressure, keeping temperature constant. So now we will do the second order derivative. So we'll differentiate it again with respect to pressure. So del square W del P del T, this will be equal to, we are differentiating with respect to P, so it will be del V del T P. Yes, because we are differentiating with respect to P, so plus P del square V del P del T. So again, these are all simple rules of mathematics. I hope you know these simple differentiation rules. So this is the product rule. So we have to differentiate P and del V del T, these two separately. So I have applied the product rule over here. If you do not understand what are the basic differentiation, all these things, please write that you do not understand it in my comment section, and then I will reply back to you how to do that. In general, I'm not making this video long, okay? I am just assuming that you guys know these basic rules. Okay, if you do not understand, then I have to make maybe a separate video on this simple rules. Okay, so please write in the comment section if you do not understand these maths. Okay, so I'll do the same thing over here. I'll do the second derivative with respect to temperature. So del square W del T del P is equals to P del square V del T del P. Okay, so I have done the two differentiations, and as I have already mentioned, in order to be dW a perfectly differential quantity, it must satisfy Euler's theorem. That is, if it is a function of temperature and pressure, these two sides del square W del P del T is equal to del square W del T del P. If this criterion is satisfied, then we can call dW a perfectly differential quantity. But you can see from this that they are not equal. They are not equal. So dW is not perfectly differential quantity. So W is also not a perfectly differential quantity. So I have proved that heat and work, they are not perfectly differential quantity. In general, most of the thermodynamic properties, they are perfectly differential quantity. So, but heat and work are not. Please remember this. Okay, now I'll introduce the concept of enthalpy. So this is one of the most important thermodynamic property. Enthalpy, we denote it as H. Okay, so enthalpy is the heat supplied to a system at constant pressure. Let me write this. So heat supplied to a system at constant pressure. This is enthalpy, okay? So what is the mathematical expression of enthalpy? H is equals to U plus PV. So please do watch my first lectures if you do not know all these terms. So U is internal energy. I have already discussed details on internal energy in the beginning. And P is pressure, V is volume. Okay. So I have also discussed that U, P, V, they are all state function. I have discussed this. What is a state function and what is perfectly differential quantity? So all three U, P, and V, they are state function and perfectly differential quantity. Okay. So H will also be the similar thing. It will also be a state function and perfectly differential quantity. Okay. Another thing I would like to mention that U is the internal energy of the system and PV, this is also an energy term. So we are just adding two energies together to get this H. So H is also an energy term. Okay. So H is the total heat content of a system, the total heat content. So change in enthalpy is denoted as dH. This will be equal to what? I'm just differentiating it. du plus pdv plus vdp. Okay, so what is du plus pdv? This is the first law. This is q plus vdp. So dH is equals to q plus vdp. So what is for if we uh, keep a P constant, so dH at constant pressure, what will be that? dP will be 0 because pressure is constant, it will be equals to Q. Okay, so this is what I have written over here, that the change in enthalpy is the heat supplied to a system at constant pressure. Okay, so this is the concept of enthalpy. So now I will discuss the how to differentiate or how to correlate H and U, enthalpy and internal energy. So please do watch my first videos to know what is internal energy of a system. So I will just try to correlate H and U. Okay. So point number one, the change in enthalpy. And this is a small change. I am denoting it as delta H instead of dH. This is equals to QP, the heat supplied to a system at constant pressure, and del U is equals to QV, that is heat change at constant volume. So this is the basic thing. heat change at constant pressure will increase the enthalpy of the system, and heat change at constant volume will change the internal energy of the system. Okay, so number 2, I will introduce the concept of molar heat capacity at constant pressure and constant volume, that is Cp and Cv. So what is that? Cp is denoted as del H del T P, that is Q by del T P. So this is the molar heat capacity at constant pressure, and the Cv is the same thing with internal energy, del U del T V, that is Q del T V. So this is constant uh, pressure molar heat capacity, and this is constant volume molar heat capacity. Okay, so these two are very important in thermodynamics. We will use Cp and Cv in many areas. Okay, so next, point number 3 is dH, the change in enthalpy, is equals to Cp dt at constant pressure, and du is equals to Cv dt at constant volume. Okay, I'm writing this constant pressure and this is constant volume. But these two expressions, they are not applicable to reversible phase change. They are not applicable to reversible phase change or chemical transformations. Okay, so this is another point to remember. And next, enthalpy is a function of temperature and pressure, whereas internal energy is a function of temperature and volume. Okay, but for ideal gas, both of these, they are function of temperature only. H is also function of T. U is also function of T for ideal gas. Why is this? Because there is no intramolecular interaction present in an ideal gas. So this pressure and volume, they will not vary. So we will just get these two as a function of temperature. Okay. But as we already discussed, that ideal situations, they are just hypothetical. They do not exist in real condition. Okay. So now I will derive the expression for Cp minus Cv. This is also very, very important. Cp minus Cv. Derive the mathematical expression of that. Okay. So let's get started on that. So what was Cp? I have already written over in my last slide. So I'm just rewriting it again here. Del H, del T, P minus del U, del T, P. Okay. So, and we also know that H is equals to U plus PV. Okay. So, we are differentiating it. Del H, del T, P. This will be equal to del U, del T, P plus or maybe I can do it over here directly. Okay, so let me erase this. So del H, del G, P, this will be equal to del Q plus PV by del G, P. Okay. So what will be this? I will just write it over here. And I'll just put this expression over here. So Cp minus Cv will be equal to del U plus PV del T P minus del U del T V. Okay. So I'm just separating it out. It will be equals to del U del T P plus P del V del T P minus del U del T V. Okay. Now we also know that U is the function of PV. So what we can write? Du is equals to del U del T V dt plus del U del V t dv. So what will be then del U del T P equals to, I'm just doing the differentiation with respect to T. So this will be del U del T V plus del U del V T into del V. We are differentiating with respect to T. So del T at constant pressure. Okay. So we will just put this expression into that Cp minus Cv, what I have written over here. Okay. So I'll put this, let me rewrite that Cp minus Cv. So Cp minus Cv, it was equals to del U del T P plus P del V del T P minus del U del T V. So it is the same thing which I got it from here. I just rewritten it. So I'll put this term over here. Okay. So what will be that? I'm just putting this expression. So del U del T V plus del V T del V del T P plus P del V del T P minus del U del T P. I have only written this expression over here. Okay, so we can cancel these two terms. So what will be this? We can take this in common. So we'll just write del U del VT plus P. We'll take this in common and del V del T P. Okay, so this is the expression for Cp minus Cv. So we know from the thermodynamic equation of state, P plus del U del V T, this is equals to T del P, del T, V. So this is thermodynamic equation of state. I will prove it later on later stage. I'll prove this. This is one of the thermodynamic equation of state. So I will put this expression over here. This expression. So I can write T del P del T V into del T del P del T V into del V del T P. This is Cp minus Cv. Okay, so I have only put this thermodynamic equation state over here. I'm rewriting this. Okay, so this is the mathematical expression for Cp minus Cv. Okay, so now what will be the expression of Cp minus Cv for ideal gas? For ideal gas. So let me write this. Cp minus Cv is equals to T del P del Tv into del V del Tp. Okay, so for ideal gas, what do I know? What is the ideal gas equation? Pv is equals to RT. So what is P? P is equals to RT by D. So if I differentiate del P del Tv, what will be that? V is constant. I'm differentiating with respect to T. So it will be R by B. Because I'm differentiating with respect to T, this will be 1. Similarly, if we do V is equals to RT by P, so if we differentiate del V del T P, it will what will be that R by P. Okay, so I'll just put these two expressions over here. So what will be Cp minus Cv is T into R by V into R by P. So RT by PV into R. Now what do I know again? PV is equals to RT. So Cp minus Cv is equals to R for ideal gas. Okay. I will discuss another point for water at 4 degrees centigrade. So what do I know? That liquid water attains its minimum molar volume at 4 degrees centigrade. We know that for water, the molar volume is minimum at 4 degrees centigrade. So if volume is minimum, what do I know from the rule of differentiation? So differentiation of dV, del V will be 0. So del V del T P it will be equal to 0. So if we put this in expression of Cp minus Cv, what will be Cp minus Cv? That will be equals to 0. Cp is equals to Cv. So for water at 4 degrees centigrade, Cp will be equals to Cv. So molar heat capacity at constant pressure will be same as molar heat capacity at constant volume. So guys, this is my little announcement on the Cp minus Cv expression. I have only derived it for ideal gas and for water at 4 degrees centigrade. In my next lesson, I will derive it for van der Waals gas and gas obeying another gas equation. So I'll continue my discussion on that. Please do watch my next series of thermodynamics if you want to know, be knowledgeable about all of the thermodynamics. Okay, and if you do not understand these things, please do watch my previous videos. I have explained in details about them. And if you have any queries, if you do not understand anything, please do write in the comment section. Okay, please do write in the comment section. I'll try to answer you, or I can make a separate video on that if you do not understand anything. Okay, so please do like, share, and subscribe my channel. So this will motivate me to make more videos for you guys. Okay, bye bye for today.